Dear learners, welcome to this video lecture session. Today's topic is control mass formulation of the course Thermodynamics and its application. I am Subhasis Maji, professor in Mechanical Engineering of School of Engineering and Technology from Indira Gandhi National Open University. We have already discussed about the first law of thermodynamics that speaks about the conservation of energy. We have discussed about the second law of thermodynamics that tells us the degradation of energy, and from the first law of thermodynamics we have understood a very important property, that is energy, and the second law of thermodynamics gives us also a very important property of a system, that is the entropy. So today we will discuss the control mass formulation for the second law of thermodynamics. After listening to this video lecture, you will be able to understand the concept of entropy generations in control mass. You will be able to derive control mass formulation. You will be able to know the concept of entropy in an isolated system, and you will also be able to explain the principle of increase of entropy. Now, dear learners, let us begin our today's discussion. We had already discussed the reversible as well as irreversible processes. Now we shall consider an isolated system which is composed of several subsystems. One subsystem is considered as control mass, and the remaining subsystems within the isolated system are considered as surroundings. The change in entropy of the control mass is to be determined. A control mass exchange energy with the surrounding by heat and mass transfer. Therefore, two types of idealized surroundings are considered: a reversible work reservoir and a reversible heat transfer reservoir. The reversible heat transfer reservoir participates in heat transfer only. The reservoir is a constant volume and constant mass, but for a reversible work reservoir will take part for work transfer only. Now let us see this figure. The composite system of control mass, reversible work reservoir and reversible heat reservoirs forms an isolated system. So in this case we have considered an isolated system which is composed of control mass and reservoir heat, reversible heat reservoirs and reversible work reservoirs, and all the subsystems are composed of a system which is known as isolated system. So there may be heat transfer in between system to the surroundings, there may be work transfer in between system to the surroundings, but in this isolated system the subsystem, that is control mass, is considered as a system, and any other subsystems apart from control mass are considered as surroundings. So there may be heat transfer in between system and surroundings, there may be work transfer in between system and surroundings for this case. We have already discussed in detail about the Gibbs equations. So Gibbs equation for a controlled volume process equal to ds is equal to du by t. And from first law, we know very well that du is equal to dq because we are considering the heat transfer. We are not considering the work transfer. So for work transfer will be 0 while considering the heat only the reservoirs which are contributing for heat transfer. So thus for the reversible heat transfer reservoir, ds is equal to del q by t, where del q is positive into the reservoir. So this heat transfers are into the reservoir. That's why for this case we have considered as positive. But the reversible work transfer takes part only work interactions. Hence, from Gibbs equation, change in entropy is equal to du by t plus p by t dv. From first law of thermodynamics, we know very well that du, that is change in internal energy, is equal to del q minus del w, is equal to minus p dv, because for this case we are considering only the work transfer, so del q is equal to 0. So ds is equal to minus p dv by t plus p by t multiplied by dv, that comes out to be 0. So for reversible work reservoir has no entropy change. The second law for an isolated system, that we all know that the change in entropy for an isolated system is always greater than or equal to 0. Now is isolated system is equal to entropy for control mass plus summation of entropy due to reversible work reservoir plus summation of entropy due to reversible heat reservoirs. Now we have just discussed that summation of entropy for reversible heat work reservoirs is equal to 0. So the equations will be for an isolated system, the change in entropy is equal to greater than or equal to 0, and since the summation of entropy for reversible heat transfer are 0, so the entropy of an isolated system is equal to entropy for the control mass plus the summation of entropy due to reversible heat transfer. The change in entropy for each reversible heat transfer of reservoir is dSi is equal to del Qi by Ti. Here we have given the subscript I, that is the case for ith reservoir, because in our diagrams we have considered two reversible heat reservoirs and two reversible work reservoirs, but there may be several heat reservoirs. So for ith case we have considered as dSi, that is change in entropy for the ith reservoirs is equal to del Qi divided by Ti, where del Qi is positive into the reservoir and Ti is the reservoir temperature, and obviously the temperature is the temperature of the boundary. Thus, in terms of control mass, del Q Cm is equal to minus del Q reversible heat transfer. Thus, substituting we get ds isolated, that is change in entropy for an isolated system, is equal to change in entropy for the control mass minus summation of del Qi by Ti Cm is greater than or equal to 0. Now you see why we are suddenly writing an expressions of summation of del Qi Ti Cm, that is control mass, because the heat is going into the reservoir. If we take as positive, so the reverse will be the negative, and that is negative heat for the control mass. This is just like rearranging these expressions in terms of the control mass, because we are interested to the change in entropy for the control mass. So the dsCm, that is change in entropy for control mass is greater than or equal to summation of del Qi by Ti for the control mass. So this is the equations we have got for a control mass for the change in entropy, that is ds control mass, that is change in entropy for the control mass is greater than or equal to summation of del Qi divided by Ti of control mass. We have derived the control mass formulations of the second law of thermodynamics. The change in entropy and S, an extensive property of the control mass, is greater than or equal to the sum of heat transfer divided by the corresponding absolute temperature of the boundary. The inequality sign is eliminated if the concept of entropy generation is introduced. Now ds minus del S is equal to 0. That means whatever the change in entropy for an isolated system minus the entropy generation is equal to 0. So we can write ds, that is the change in entropy, minus del S generation, that is the entropy generation for an isolated system, is equal to 0, and we can write that ds Cm, that is change in entropy for a control mass, minus the summation of del Qi by Ty control mass minus del S generation, that is change in entropy generation, is equal to 0. Or finally we can write that del S generation is equal to ds Cm, that is change in entropy for the control mass, minus summation of del Qi by Ti control mass is equal to or greater than 0. So this is the entropy generation by the process. But while discussing for any thermodynamic analysis, whether for the steam power plant or refrigeration air condition or vapor power cycle or gas turbine cycles, our main motto is reducing of entropy generation, because entropy generation is nothing but disorderliness or randomness of the system. The equation for the control mass can also be written as ds control mass is equal to d integral of rho small s dv greater than or equal to summation of del Qi by Ti of control mass. So here S is written as small s into rho dv, that is small mass dm. So dm we have considered as rho into dv because mass is nothing but density into volume. So if the control mass has a uniform distribution of mass, so finally we write that d within bracket m into s of control mass is greater than or equal to summation of del mqi by Ti of control mass. So you can just eliminate m from both sides. Finally we get that dscm is greater than or equal to del small qi by Ti of control mass. The equation for control mass can also be written as in terms of the entropy generation. So entropy generation, that is del S generation, is equal to d within bracket integral of rho dv minus summation of del Qi by Ti of control mass is greater than or equal to 0. So for irreversible process, del S generation, that is change in entropy generation, is always greater than 0, but for a reversible process there is no entropy generation, so change in entropy generation is 0. So here for this equation can also be written in terms of intensive basis, that is del small s generation is equal to del small s control mass is minus summation of del small Qi by Ti of control mass greater than or equal to 0. Now the equation for control mass forms of the second law can also be written as in terms of rate basis. Now ds by dt of control mass, that is the rate of change of entropy of control mass, on rate basis is equal to d dt of integral of rho s dV of control mass greater than or equal to that summation of q dot I. Q dot I is the rate of heat transfer divided by Ti of control mass. And same we can write for the entropy generations, that is rate of entropy generation, that is S dot generation is equal to d dt within bracket integral of rho s dV of control mass minus summation of Qi dot divided by Ti of control mass. This will be greater than or equal to 0. But here we are taking Q over dot means the rate of heat transfer. Now the equation for the control mass forms of the second law can also be written as on rate basis, that is ds by dt is equal to ds by d dt of integral of rho s d greater than or equal to summation of q I by Ti of control mass and S generation minus d dt of integral of rho s dV of control mass minus summation of Qi by Ti of control mass greater than or equal to 0. If the process is reversible, then of course entropy generation is 0. So ds, that is change in entropy for the control mass reversible, is equal to that dCm reversible equal to summation of del Qi by Ti. So this is the case for the reversible process. The equation for the control mass forms of the second law can also be written as for a single heat transfer. We can get that is d change in entropy for control mass reversible is equal to d del Q by T. Here we are considering only a single reservoir. So summation term will not be there over here. Summation term will only be there for several reservoirs are participating for heat transfer. But if there is only one heat transfer, we can write the change in entropy for a control mass for a reversible process is equal to del Q by T. But from the first law of thermodynamics, we can get this expression, that is del Q reversible is equal to TdS, and we can get further equations if you consider the first law of thermodynamics, and if you can write the del Q for some other forms. The equation for the control mass forms of the second law can also be written as heat transfer from state 1 to state 2. We get 1 Q2, that is the heat transfer from state 1 to state 2 is equal to integral of TdS from 1 to 2, or if you take on the basis of per unit mass basis, so 1 Q2 reversible is equal to TdS. Here we are taking small s, that is the equations for the intensive basis. Now we will discuss some important statement of del Q by T. First we will discuss the statement 1 given by the Clausius. So these are known as Clausius inequality statement. So when a system executes a cyclic process, the integral around the cycle of del Q by T is less than or equal to 0. This statement, popularly known as the Clausius inequality statement, can be symbolically written as cyclic integral of del Q by T less than or equal to 0. So this is the Clausius inequality statement, that is statement number 1. Now let us discuss about the statement 2. When a system undergoes an internally reversible cycle, the integral around the cycle of del Q R divided by T is always equal to 0. This may be symbolically written as cyclic integral of del Q R by T is equal to 0. Here R is known as the internally reversible process. Now let us discuss about the statement 3 of Clausius. When a system undergoes a change of state, the value of integral is independent of the path between the given two states. In other words, suppose a system can undergo from state 1 to state 2 through several reversible processes, for example, path A, path B or C, then the value of integral from state 1 to 2 del q by t to t between state 1 and state 2 is the same for each reversible path. Entropy S of a system is a property whose change between two states 1 and 2 is given by del S is equal to S2 minus S1, that is integral of del QR by t from 1 to 2 at ds is equal to del QR by t. Entropy as qualitative test for irreversibility. So we know very well that change in entropy for an isolated system is greater than or equal to del Q by T, and for a reversible process, that is ds is equal to del Q by T. For irreversible process, change in entropy is always greater than del Q by T. Now let us discuss about the principle of increase of entropy. Now, if you consider an isolated system, and in the isolated system, let us see that there are several subsystems are there, and one subsystem you can consider as a control mass, and the remaining subsystems you can consider are the surroundings. There may be heat transfer or transfer in between the other subsystems within the control mass for which you are interested. Now see, for a irreversible process, the del S for system plus del S for surrounding is greater than 0, because if the process is on, there will be change in entropy for the system, and simultaneously there will be change in entropy for the surrounding also. So for irreversible process, the change in entropy for the system plus the change in entropy for the surrounding is greater than or equal to 0. For a reversible process, the change in entropy for the system plus change in entropy for the surrounding is equal to 0. But a process is impossible when del S system plus del S surrounding is less than 0. So change in entropy for the system plus the change in entropy for the surrounding for an isolated system can never become less than 0. Now in this diagram you see there is a hot body, there is a cold body, and there is a heat transfer from the hot body to the cold body. So for the hot body, since there is a heat loss, so temperature will reduce in the process of heat transfer, and there is a decrease in entropy. And the cool body, it will receive heat from the hot body due to the heat transfer. And for the cool body, since temperature is rising, more randomness, more disorderedness of the system will be there, and the entropy will increase. But if you see the combined system as a whole, then the change in entropy for the isolated system, which is combining both the subsystems, one is hot body and another one is cold body, the entropy, net entropy will increase for a reversible process. But for a reversible process, the final entropy will be same as the initial entropy for the whole system. So if the physical process is irreversible, the combined entropy of the system and the environment must increase. So entropy means it is the property which describes the randomness, disorderedness, uncertainty of a system, and this property comes out from the second law of thermodynamics, which tells us the direction of the process. So in an isolated system, change in entropy is always greater than or equal to 0. So S final is greater than S initial for a irreversible process, and S final is equal to S initial for a reversible process. Entropy, that we have already discussed, is the measure of disorder or randomness of a system. The entropy S is an extensive property, must always increase or remain constant for an isolated system. So change in entropy for an isolated system is always greater than or equal to 0, but so we can write S final minus S initial for an isolated system is always greater than or equal to 0. Reduction of irreversibility is the goal of many analysts. For an isolated system, for irreversible process, that S final is greater than S initial, that means there is an entropy generation. So entropy generation can be defined as S final minus S initial, and for a reversible process, entropy at final stage is equal to the entropy at the initial stage, but for a reversible process there is no entropy generation, because entropy generation is defined as S final minus S initial. So for a reversible process there is no entropy generation. Irreversible process generates entropy, whereas reversible process does not. Total reversible means system and surroundings delta S generation is 0. Complete irreversible system is an idealization such as frictionless pulley or ideal gas, etc. But the process which we deal with, like heat transfer for any process like heat exchanger, nozzle flow, and for steam power plant, for analysis of gas turbine power plant, those processes are not reversible, and we will discuss in detail later on for those processes